time. Oh, I need to select this. Oh, forgot to change this. Okay. Any question from this time? Hello. Wait. Hello. Okay. Any question from this time? So this time we start talking about actual quantum computation, and we go through a lot of things. Let's use this. Yeah. So we go through this quantum circuit model. It's like classical circuit model where you have wires carry your information on your qubits, and you have gates that do the transformation that you want to do. And there's a time flow from left to right. But there are extra elements in quantum computation that are those measurements. Measurements we will be doing at the end of the circuit. And for simplicity, we assume all the measurements are just done in computational basis, because we have shown previously that if you want to do any generalized measurement, you can just do computational basis measurement and do some unitary transformation with some ancilla before the end of your circuit. You can get the same measurement outcome. So quantum circuit, wires, unitary gates, and measurements. And then there are these two extra things quantum circuit need to obey. So first is quantum circuit cannot have fan out because there is no cloning. So you cannot have one wire split into two wires that carry the same information, because that's just not possible information theoretically. And also every gate needs to be unitary, and that means they are reversible. So for every gate, there must exist another gate that totally reverse what this gate do. That's not true for classical, because classical say you can have AND gate, and you lose some information, and that's not reversible. Then we go through quantum gate set. There are our familiar friends, so Hedema and poly X, poly Y, poly Z. Then there are less familiar phase gate and this T gate, which are square root of, so S is the square root of Z and T is square root of S. Then there are two qubit gate, and the one we use most is the CNOT gate. This is a classical gate because you see it just map computational basis state to computational basis state. So this is basically a classical gate that we linearly extend to become a quantum gate. And as we said, on computational basis state, this is just like classical CNOT. So there is a control gate, control qubit, and there is a target qubit. So on computational basis, if control bit is 0, then this gate do nothing. And if control bit is 1, then you apply a NOT gate on the second qubit. So basically doing this O plus 1. So this O plus, we are going to see this throughout this whole chapter, and actually throughout the whole class also. This O plus means addition with mod 2. Actually depends on what is registered, but usually it means mod 2, but sometimes it's mod n. Okay. Anyway, it's addition in some field, addition modulo something. Usually it's mod 2. And anyway, then we have CNOT. CNOT can be written as so we can write down CNOT on computational basis with this nice formula. CNOT AB become A and B O plus A. And now we have other gates. We have we can have arbitrary control unitary that does nothing if the control qubit is 0 and apply this unitary if the target is 1, controller 1 is 1. And in particular, there is control Z. Control Z has this spatial symbol that looks symmetric because it is very symmetric between its control qubit and target qubit. Because you write down its matrix, you find out it does something only when both the control target are 1. When both the control qubit and the target qubit are 1, you apply a -1 phase. And then there is the swap gate, which is actually also pretty classical. You just swap whatever is up here to whatever is down here. Okay. And there is a homework problem, asks you to show that this very classically defined swap gate actually also swap quantum states. Then there are gates that affect more than 2 qubits, and basically the only one famous enough for us to talk about is this Toffoli gate, which is also classical. It is control NOT. So we apply a NOT gate on the third qubit only when both the first qubit, only when both target qubit, you only apply a NOT gate on the target qubit only when both control qubits are 1. So you have this A times B here. And A times B equal to 1 only when A equal to 1 and B equal to 1. And we like to talk about it because it's reversible and universal for classical computation. So it has some theoretical use. And we have HR notation that you might sometimes see on paper or the book. That is this hollowed control. So if you have an empty circle, then it means it's control on 0. So you do this unitary only when this control qubit is 0. So those are gates. Then we go through lots of examples of quantum circuit. And the circuit you can refresh them yourself, and you have lots of practice in your homework. But I guess something to note is that you don't want to multiply out, although it's possible you don't want to multiply all your gates in the 4 2n by 2n matrices. So I guess the general theme that a general principle of how you solve this problem is that you do multiply out all your states. Right? So you basically write out your states in summation in computational basis. Then you try to apply your quantum gate 1 by 1 using relationship like this. So you write down your gates in computational basis, and basically all the gates we talk about has pretty nice representation on computational basis. You see, we all see how they act on computational basis. So you write down the states in the 4 computational basis, then you apply gates 1 by 1 using principle like this. Using this principle where A times B. So you have A tensor B on side and phi, then it's A phi on B side, and usually you have lots of B equal to identity. So say here you have this Z gate is basically Z tensor identity. Then you see this B part don't get changed, and you just apply Z gate on the A part. Something like that. So easier way to say this is you write down your state in the 4 bases, then you apply your gates to the slots that correspond to the wires. Okay. Okay, and we see through this superdense coding interpolation example once again. So, question on this quantum circuit model? If not, okay, then we have this short page of quantum universality. So there are some set of quantum gates that are universal for quantum computation. So the most standard one is this C0, HEDMA, and the T gate, and it's quite cool. We will probably skip this because it takes a lot of time and don't talk too much about algorithm, but it's a cool story you can check out. You can check out the book, and we will also post a slide that corresponding to this, but we'll probably not spend time talking about details. So that's pretty cool. And okay, then we switch gear and we start to talking about quantum algorithms. And quantum algorithm, we'll want to see the speed up. So we start talking about this a bit weird concept of quantum oracle. And this is actually generalization of classical oracle. But and this oracle idea is you have some f of x. For now, we think of this as some sub-algorithm that might be quite costly to compute, but you can compute it. Okay. So it's some sub-algorithm, and you have input x and will output f of x. And then you can think about this sub-algorithm in some kind of unitary. You put it in your quantum circuit. And it should be in this form where there is some input register and it's their input register. And then there is an output register where you write down your answer f of x here. Yeah. And this is unitary in this form because you want your quantum circuit to be reversible. And you can see that if you think, you can think a little more about why this will guarantee being reversible. And but something that's not reversible is you have input x and it becomes f of x. So in classical circuit, you probably just want this kind of thing as your oracle. But for quantum circuit, this is not reversible. So it's impossible to have this kind of oracle. And yeah, but okay, so there is some annoyance needing to make this reversible, but there is also a good thing about quantum oracle, that is it now supports quantum superposition. So for example, we are going to see very soon that you can put this input and also this output as a non-computational basis state, so superposition of something, and this will give you some quantum advantage. And here we have easy example here. So we have plus state up here as input, and let's say we put a 0 as in the record register at the beginning. Then you apply this u of f, and it should compute both the 0 part and the 1 part of this f of x in superposition. So the input to this UF will be 0, 0 plus 1, 0. Then you see how 0, 0 gets changed by this UF. It follows this formula. So it becomes 0 and f of 0. And then this 1, 0 becomes 1 f of 1. And because everything is linear and works in superposition, so the end result is 0 tensor f of 0 and plus 1 tensor f of 1. Question? Okay. And for now, let's say f of x is Boolean function. Although at the end of the slide, you will see some example of f being non-Boolean. But for simplicity, let's assume f is Boolean now. That means the record register only have 1 bit. and this O plus here is plasma 2. Okay. And okay, finally, we can go. Yeah. Any question? So that's the end of recap about what we talked about last time. And if not, then finally we can go into our first quantum algorithm. So George's algorithm. It's an oracle algorithm. So once again, we think oracle as some kind of sub-algorithm. And then we want to compute something on top of this sub-algorithm. And okay, let's switch to here because we fix some typos. Okay. So the sub-algorithm we want to compute is, we want to compute f of 0 O plus f of 1. So this is basically the parity between f of 0 and f of 1. You can see that, let's just write down this. And well, so first, we assume our f is a very small function. It's 1 bit input, 1 bit output function. So there is actually only 4 possible f. So input of f is only 1 bit, output is only 1 bit. So there are only two possibility. And so this f of 0 plus f of 1 is 0 if both of them are 0. So 0 and 1, or if both of them are 1. Then f of 0 plus f of 1, then this gives you 0. And if it's 1, 0 or 0, 1 here, then this addition gives you 1. Okay? So what we want to determine is, the other way to describe this is want to say whether f of 0 equal to f of 1. Okay? Anyone okay with this setup? And here f is given like a sub-function, sub-algorithm, or more theoretically it's given as a black box. So we cannot look up the inner working of f. We can just put f as a box somewhere inside the algorithm. And we want to see how many of these boxes we need to put in our algorithm to determine this value. Is f of 0 or plus f of 1. And in this algorithm, we'll see that quantum oracle is more useful than classical oracle. And superposition is being useful. Okay. So let's talk about classical oracle first. So, well, how many queries you need to put in your classical algorithm to compute this f of 0 and f of 1? Well, you need 2 queries, and the proof is kind of easy. You just list all the case. There are not many things you can do here in classical algorithm. So you can look up f of 0 or f of 1, but obviously if you only look up one of them, it's not enough to determine this O plus thing. Whatever you look up. Yeah. So you need 2 queries here, and obviously 2 queries is enough. If you look up both of them, then obviously you can just, those 2 answers, then you add them together. Then that's how classical algorithm works. But the quantum speedup we see is that in quantum we can kind of look in superposition and look in a different direction and only do this in 1 query. Okay, so let's jump into the algorithm. This algorithm look at this. And yeah, so in the middle is our favorite query. So you have f here, and there is our input register or record register, and actually we don't need any other ancilla, so just those 2 registers, those 2 qubits into our f, but with some other gate. So the gate is, so those h are our favorite head mark gate, and this x is a NOT gate. Okay, and why does this work? Well, let's see how the state evolves throughout the circuit. So let's first see here. Okay. So before our unitary, we basically there is no two cubic gate, right? So basically state about that state. So the first register is going to get hit by a headmark. So 0 get hit by headmark become pass state. And the second register, so what we want is we want to create a minus state here. You will see the reason very soon. So what happened here is we want to create a minus state here, then we first hit 0 with x, so it become 1. Then hit this 1 with the header bar, then become minus. So at this point is plus or 10, plus 10 is minus. It's plus here and it's minus here. Okay, clear? Okay. And we actually want to view plus as a superposition between 0 and 1 because this makes our analysis how UF works easier. So we write this plus as 1 over square root 2, 0 plus 1, and the second register is minus. Okay. So now the interesting part happened. So why do we want the minus state here? Because we are going to apply this fixed kickback technique here. Okay, let's see through the math first. So how this math kickback works? So let's see how UF what UF do when your first register is some x, so this x is actually computational basis. Okay, didn't say, but so you have some f in computational basis, and then a minus on your recorder register. And okay, then we write. Then we know the minus is 0 minus 1, right? 1 over square root 2. You can once again write this minus as computational basis 0 minus 1. And then this UF, okay. So actually have a extra step here. It's really slow. Okay. So this is UF and X. Let's write this. Okay, it doesn't matter. UF 1 over square root 2, then X 0 minus X1. Okay, so just writing minus as 0 plus 1. Oh, sorry, 0 minus 1. Then you apply UF on those two things. So X stay on as X, but and as we said, UF will add f of x onto the second register. So we have O plus f of x on 0, and then O plus f of x on 1. Okay, so this is just apply UF on both of these, and then they stay linear. And so what is this thing? What is this whole thing when you consider f of x being 0 or 1? Well, obviously f of x is 0, then nothing happened here, so this actually should stay as minus state, right? Because nothing happened. But f of x equal to 1, then this become 1 minus 0 instead of 0 minus 1. And that's basically the same state, but we get an extra minus sign, right? Because you swap it between this 1 and 0, but there's a minus sign here. Okay? So, clear? So, with this minus sign here, that's very important. Okay. So, is XO tensor, the minus state, both of them, but when f of x equal to 0, there is no minus sign here, and when f of x1 equal to 1, there is a minus sign here. And we can write this in a more succinct formula. So there is minus 1 to the f of x, and XO tensor minus. Okay, so you see that the information of f of x now become encoded in this minus 1 to the f of x phase. So if f of x equal to 1, you got this extra phase. If f of x doesn't equal to 1, you don't have this extra phase. Okay? So this is called phase kickback. So you see a phase here, and why is this called kickback? Because you see now this extra second register kind of doesn't matter, right? It started as a minus state, and it ended as a minus state, and it has no entanglement with the first qubit, whatever. Okay? And everything now just become, and phase is kind of a global thing, right? Because you remember the tensor product structure, this phase don't need to stay on the second register. Phase can be like, you can stick the phase to the first register also. And so this is really nice because we make our problem a lot simpler. We can kind of ignore the second register. You just stay as minus state all the time. And what your oracle do is you will apply a phase depending on your oracle value, your function value. Okay? And this is a really cool technique, phase kickback, and we'll see this all the time through our quantum algorithm. And obviously, this is only possible for quantum algorithms because for classical algorithm, there is no such thing as phase, right? Okay. So, any questions so far? Do people understand how we calculate this phase kickback result? Okay, assume you all understand. And then we see how this phase kickback actually works. Now remember our psi 1 equal to this thing. So then now apply UF on our psi 1, which as we say is 0 tends to our minus state and 1 tends to our minus state. And as we calculate here, so the minus state just stay minus state. But now we get extra phase depending on our function. Okay? So if 0 here, 0 as your x, then you have minus 1 to the f of 0. And you have 1 as your x, then you have minus 1 to the f of 1. Okay? And then then we just do some math manipulation. So we can take out a global phase. So let's take out minus 1 to the f of 0 factor here. And so then then this is 0. Okay, so yeah, so firstly let's take out the tensor minus because everything is tensor minus. So let's just write down the tensor minus down here. Then then we take out the global phase of minus 1 to the f of 0. So this part don't have phase anymore. But now the relative phase becomes minus 1 to the f of 1 minus f of 0. Okay, that's just arithmetic. And well, what's this? Now, what's this state? Well, it depends on the difference between f of 1 and f of 0, right? So if f of 1 equal to f of 0, then this will be a plus state, right? Obviously, because this is 0, this difference is 0, and this is a plus state. And f of 1 not equal to f of 0, then the subtraction is either, because they are either 0 or 1, so it's either plus 1 or minus 1, right? Whichever is the case, minus 1 to the 1 is minus 1, and minus 1 to the minus 1 is minus 1. And this will be 0 minus 1. Okay. So this will become the minus state. Okay. So you have a global phase that doesn't really matter for -1 to f of 0. Then your first register, you will be either plus state or minus state, depending on this parity of your f of 1 and f of 0. So you see we are getting what we want. We are distinguishing whether f of 1 equal to f of 0 or f of 1 not equal to f of 0. And there is all tensor minus. Okay. So that's what happened at this part of the algorithm. And finally, at the last part of algorithm, well, basically we don't do nothing. We do a head mask, so we'll just turning this plus and minus to a 0 and a 1, so we can do measurement. Okay, because we measurement in computational basis. So at last part, we do a head mask on this register. This becomes 0 and 1. And we see that when we do measurement on this register, we we get outcome 0 if f of 1 equal to f of 0, and outcome 1 if f of 1 not equal to f of 0. And this is exactly what we want. This is our f of 0 or plus f of 1. Right. So you see that we can only use one query to get this addition, modular addition between f of 0 and f of 1. Or sometimes this is also called parity. Okay. Parity between f of 1 and f of 0. So any question about our first quantum algorithm showing possibility of quantum speed up? Yes? No? Yes? No? Okay. Yeah. So, yeah. Once again, this phase kickback is very important. Please get familiar with this and remember how it works. And you should see this. Do we see in midterm? Maybe. You might see it in final again. You probably see this in midterm. Yeah, this is the basis of a lot of quantum algorithms. And I don't know. Sometimes we go very high level. Sometimes I don't feel it's strictly necessary. But one thing you definitely do is it make analysis a lot easier because you just have one less register. Remember, in quantum everything tensor together, and the more qubits you have, the more annoying, the harder your analysis get exponentially. But if you use phase kickback here, you see the second qubit just stay as minus state, and basically you don't care about it. You just care about how the first qubit change with some phase that depend on your function value, right? So that's pretty cool. Okay, then that's okay. So kind of as expected, we probably won't have time to talk about second algorithm because we want to talk about some more theoretical thing. So let's talk about quantum query complexity. And so this is another complexity thing that we missed in the classical algorithm part because well, we don't quite have interesting example of classical query algorithm. Anyway, so let's talk about quantum or classical query complexity. So as we see, we have now been thinking about some black box function f of x that kind of represent your subalgorithm. And f of x, as we say, we usually think then as a Boolean function. So it is function mapping some n-bit string to small n-bit string to 1 bit. And as we said, you can also think this f of x as some kind of input to our bigger problem that we want to solve. what are the on the truth table of this f of x. So this small n bit function, we can have a one-to-one correspondence to a big N bit string. So big N is 2 to the small n. And the correspondence is pretty simple. You just write down the truth table of this f of x. There are 2 to the n possible input value. 2 to the small n possible input value to this f of x, and each one of them has 1 bit possible output. So you write down this f1, f2 to f of 2 to the n, and well, we see here you get a big N bit string, right? And when we do query on this f of x, we basically look up locations on this very long input string, right? You can think about querying this f of x as looking up the location of this input string. Well, at least for classical query. But for quantum query, as we just see, we can kind of look different position, looking at different positions in quantum superposition, and so back to talking about query complexity. So quantum query complexity is the minimum number of queries. Okay, so we think about what's the number of queries you need to put in your algorithm to solve the problem. So you want to compute something. And something should be dependent on f, right? Because the query, you care about how many information you need to get out of f to compute the thing you want to compute. So for example, in your DOH algorithm, we want to compute, or this DOH problem, we want to compute this f0 or plus f of 1. Okay. We don't want to know everything about f, we want to know something. Usually also 1 bit. Yeah. And but the trick here is this is a different kind of complexity than we talk about. So in the previous chapter, when we talk about classical complexity with A, we care about time and space, right? So here we basically don't care about time or space. We care about number of queries, and this is I would say an approximation to the time complexity. So the justification is usually we say this U of f is like a very costly subalgorithm, and so most of the time spent on your algorithm is how many times you need to call this subalgorithm. So we think about query complexity as an approximation to the time complexity. And also a very practical issue is that computing this query complexity is easier than computing time complexity. Because time complexity, when you actually want to bound them, is pretty hard. But when you think about query complexity, then there are a lot of information thing you can do. Then you can actually give a rigorous lower bound to query complexity. For example, here this f of 0 plus f of 1, we can just say if you look at f of 0, then you still don't know this thing, so it's pretty easy to see that classical query complexity here is 2, etc. Okay, and let's go back to this picture. So the number of query is the only thing we care about. So sometimes we'll have this mental picture of a query algorithm. So there is some input, and the initialize with O0 doesn't really matter. And then there is unitary, whatever you do, we don't care about it. It can be arbitrary unitary, because the only thing we care about is the number of oracle, and I should use this, right? So let's use gold because oracle are what costly. So what we care about is we will place some oracles in our algorithm. So the only thing we count is the number of oracle you put in our algorithm. So here it has 3, but maybe more in the middle. And okay, so we will place some oracle in your algorithm, and your complexity is you only count about how many of these you use. In a general algorithm, so there are other things you might do, but we think they don't cost about anything. So you can place the arbitrary unitary between your oracles. So your algorithm should be, you start with 0, 0, then you apply whatever unitary you want to do. But the point is that this unitary doesn't depend on f, right? So f is, once again, f is kind of the input now. So you have some layers of unitary that doesn't depend on your f. And so you start with doing this unitary, then apply your oracle, then apply another unitary, whatever unitary that doesn't depend on f, your oracle, etc. And at the end you do the measurement, and hopefully you get the thing you want to compute about f. So for example, what we had there is we compute. So in our George, I guess in our George problem, then we can compute f0 plus f1, right? That's what we'll want to compute at the end. And I guess we can also see. So in terms of this layered picture, so it's a very general thing, right? So in terms of a layered picture, you can see here we have 3 layers, right? So we initialize with 0. Then you have this whole thing as your U0, then you have our UF here, then you have this U1 here, then you do measurements. Okay. So this is just a very general picture. You can see this U can be actually pretty complex. Okay, and as we say, so why would want to do this? Because this is an approximation to time complexity, but actually bounding time complexity is hard, so we study query complexity. Okay, and the idea is there are some hard part of the algorithm that you just abstract into this subalgorithm U of f, and we want to count how many of these hard parts you need to do. And usually it works out pretty well. You will see later in our class that it works in the 2 main quantum algorithm. We talk about the global algorithm and the Shor's algorithm. Okay, so this works in a lot of time, but there are also a lot of examples of this doesn't work. Well, and yeah, then you need to think harder about how to achieve matching time complexity. Yeah, but yeah, but still studying the query complexity is pretty fun. There are lots of interesting mathematical structure. And then finally, there is a interesting thing that only happen in quantum query. So for quantum queries, you can always do phase kickback. And I believe this is also a homework problem that you can prove. Not sure. And that is, we'll define 2 types of quantum oracle. So, so the thing we have defined up there the so the thing we did up there, so UOL of x, y equal to x and y o plus x, o plus f of x. This is, I guess, standard basis quantum oracle, but a lot of time people just talk about the face version of quantum oracle. So we will use the notation of u tilde f, although a lot of time people don't even write this u tilde. And there is a face version of the oracle because we think about you have input x and you will basically give you f of x in this phase, the -1 to the f of x. But it's a little more complicated. So you see C here because this C is actually a control register, and you can think about what is needed. But for this u tilde to be equivalent to this UF, this C is needed, and this C is a control register. What you do is if C equal to 0, then this UF tilde always do nothing, right? Because if C equal to 0, then you always -1 to the C times 0. So this is always nothing here. Yeah. And when C equal to 1, then you actually do this phase kickback. Yeah. And it's one homework problem to show that those two things are equivalent. So equiv 1 to 1. So when we say equivalent means 1 UF tilde you can simulate 1 UF, and 1 UF can simulate 1 UF tilde. Okay. So you can think about how that's possible. And that's finishing our complexity talk. Yeah, so let's have a small comparison between classical and the quantum query. And so there we are both thinking them as some black box to some function f of x. So some kind of black box implementation of your subalgorithm, let's call it. And classical is much simpler. You can think of it just as one register because you don't need to satisfy reversibility kind of thing. So you have some input x and you go through this black box, you give you f of x. And yeah, so you don't need to be reversible, and because you can just copy this x somewhere you want, so you also don't need to keep this x. Okay, and it's using classical circuit obviously. And as we said, the quantum oracle, so the computational basis version, you have two registers, x and y. So the input x stay input x at the end, and the output register y, you will write your output f of x here, but everything needs to be reversible, so actually you have y plus f of x here. Okay. So the y don't get erased. And once again, you can do quantum superposition on this, because if you say you have some x1, y1 plus x2, y2 as the input, some entangled input to this u of f, then you get some probably still entangled output, x of y1 or plus f of x1, and x2, y2 or plus f of x2. Yeah. And then there is comparison between classical and quantum query. Yeah, okay. So classical quantum complexity is also an interesting research area in computer science. But for quantum computation, we want to compare between classical query complexity and the quantum query complexity. And one thing you can see pretty easily is one quantum query is more powerful than one classical query, because whatever you want to compute here has more information. You can just put computational basis state, put 0 here, then it give you f of x out here. Okay, so one quantum query is always bigger or equal to one classical query, and A way to say this is quantum query complexity is also less or equal to classical query complexity. Okay, but now the question is, what's the possible gap between quantum query complexity and classical query complexity? So that's the thing we want to study, and people are still studying, but we're going to see some known and interesting results starting next class. So today we already see a very small separation. Okay? So for this George problem or George logarithm, it shows that we have something that requires two classical query and to solve, but only one quadrant query to solve. And next time we'll see this George algorithm. Okay. Keeping bigger separation. Any question? Otherwise, let's start again on Thursday. And yeah, let's start again on Thursday.